Okay, let's go over A, B, C1, and C2 from Codeforces Round 708 Division 2. The first question is basically you're given an array and you want to find an ordering of the array such that the sum of all of the mexes at each index is maximized. And what is a mex? So like what is a prefix and what is a mex? A prefix of the array is a subarray starting from the beginning and ending at index I, and the mex of that prefix is the first uh, non-negative non-negative number which does not appear in the array. So for this example, the mex of 1, 2, 3 is 0, and the mex of 0, 1, 2, 4, 5 is 3. And so you want, like basically if you're given an array like, let's just use their example, 4, 2, 0, 1, 3, 3, 7. You want to reorder it such that like if you take an I, the prefix up to that I is the mex of the prefix of that I. If you sum them all up, it's going to be minimal. Sorry, it's going to be maximal. And so basically the idea behind this is that like the mex, like it just depends on the minimum number that is not in the not in the array. So you're always better off sorting the array because that's basically the only way you can maximize the mex, right? So let's just say we try to sort this array. We get 0, 1, 2, 3, 3, 4, and 7. And then this is pretty good, right? It gives us like if we add up the sum of the mexes, we get 1 plus 2 plus 3 plus 4 plus 4 plus uh, 5 plus 5, right? But this isn't optimal because if you notice, we could have exchanged this 3 and this 4 to get an even higher value, but that's because this 3 is already here, right? And like so from seeing this, we can kind of say that like once we've seen a number already, like we don't need to keep adding it in the sort because like we're better off picking a higher number because the calculation of our mex like already took care of that number. So what ends up being the optimal algorithm is to basically just put down all of the unique numbers first in sorted order, and then just put just put whatever is duplicated at the end, and then and like it doesn't matter which which places you put the duplicated numbers. Like they can be like you can have 3 and let's say 7 was duplicated. Like you could put them in sorted order, or like you could put them in reverse sorted order, or like it doesn't really matter, right? So yeah, that's the algorithm for solving this problem. Basically, you put all the unique numbers in sorted order first, and then you put everything else like at the end. And yeah, I would yeah, I guess I can show my code real quick. Give me one sec. Uh, yeah, so the way I did it was yeah, I sorted the array, and then like I had a set of numbers that I've seen so far, and if I haven't seen it, I push it back to my part 1 vector. If I have, I push it back to part 2, and then at the end I just kind of print the numbers out in sequence. Cool. So let's go on to problem B. Yeah. So this problem statement is that you're given an array, and you're also given an integer m, and you want to divide elements of this array into some arrays, into some subsequences, such that like either the length of the subsequence is 1, or for each adjacent element, like the sum of any two adjacent elements in the subsequence is it is divisible by m, basically. And so if we look at this example, like this is their array, and then here they broke it up into these three subsequences. They picked 4 and 8, and then m here is 4, I think. Yeah, m here is 4, so 4 and 8 work because 4 plus 8 is divisible by 4. 2, 6, and 2 work because 2 plus 6 and 6 plus 2 are divisible by 4, and then 9 works because it's of size 1, right? So yeah, that's the problem statement. And when thinking about this problem, especially thinking about in terms of divisibility by m, instead of actually looking at these numbers in the array, it's easier to look at these numbers mod m. So that's the approach we're going to take. Right. So let's just say let's just suppose m is 4, right? So what can this ai value be? So ai can either be 0, 1, 2, or 3. Mod 4, right? So let's just write down a random array and try to think about this, right? Yeah. Let me just do. Let me just draw more zeros. Right. Okay. Cool. The first thing to notice is that, if you look at all of these numbers, mod m, very clearly, if we just try to come up with an upper bound for what. So oh, I forgot to mention what the question was asking. The question is asking for the minimum number of these subsequences that you can make from this array, such that each one either has length 1 or has a bunch of adjacent elements which whose sum is divisible by m, basically. And so very clearly an upper bound to the answer is just n, right? Because in the worst case you can just have all of these numbers be its own subarray. But that isn't optimal. And if you notice, if we look at these numbers mod m, it's clear that if we look at the numbers mod m, the analog to a sum dividing by a sum being divisible by m is basically if the two numbers add up to 0 mod m, right? And so very clearly we can see right away that that we can just group all the zeros together, right? Because anytime you add two zeros together, their sum is going to be 0 mod m. Great. And so the next thing we can do is then for each element, basically, we look to let's say that we look at 1, right? Let's say we have a hypothetical subsequence starting at 1, right? And so because we're looking at actually 1 mod m, if we wanted this array to extend for more than one element, we would need to add something else to this, and that there's only one choice for that number, and that is 3. Assuming m is 4, because 1 plus 3 is the only thing that can equal 0 mod 4, right? And then let's try to extend this further, right? So yeah, so let's say we're at 3 and we want to extend this list to the right. So the element we add to this list needs to be when added to 3 needs to be equal to 0 mod m. But there's only one element which fits that criteria, and that element is 1. But now we're back to 1, and so we need to add 3 again. and then basically it just comes down to this, right? And in general, uh, and in general, so like we've discovered the case where it's 0, right? There's a second case where like you basically need to go something like a minus a minus a. So like sorry, this is actually a mod m minus a mod m, and so on. Uh, just yeah, just repeating. And so here, and also that's the best we can do. So here, what we can do is we can see that like there's there's a 3. Sorry, there's a 1, right? It can only be matched up with 3s, and 3s can only be matched up with 1s. So let's just group all the 1s and 3s together and turn this into another list, right? And this list can be something like 3, comma 1, comma 3, comma 1. Great. And then finally, this mostly works except for like when implementing things. Like you also need to keep track of these 2's, right? So the third case is when like your number is equal to m over 2 mod m, and also m is even. And at that point, like what you do is like you can just group all the 2's together, right? The So basically like the number is self-inverse, and so you basically just need to group all of these numbers together. And yeah, that's so like these 3 cases are basically all you need to actually come up with the perfect yeah, like uh, with the optimal solution. And basically the solution is the algorithm which I chose to do is to keep along counters, right? So I count like how many things, like how many numbers I've seen. Let's say let's just continue with this example of m is 4, right? Let's say I saw 10 zeros, 10 ones, 10 twos, and only 5 threes, right? So here I see 10 zeros. I know I can group them all together, so I add 1 to my result. And then I look at 1. 1 can only pair up with 3 because it falls into this case 2 here. And then like if you think about it, like you can only do one more than the minimum of these 2 guys, right? Like you can only like you can pick 5 threes from your list, and then like let's say you pick 5 threes, right? Then you can pick 6 ones and have a proper list. And so basically what you can do is like you can add 1 and then remove 6 and then sorry re- remove remove 6 from here and then remove 5 from here, and then just and then that kind of represents this 1 3 1 3 1 3 1 3 1 subsequence that we formed. And then there's 4 leftover ones. Like we have like there's like we're guaranteed there's no way that we can put them into a subarray of size greater than 1. So what we do is we just make size 1 lists for these guys. And then here like we have the case where the number is equal to m over 2 mod m, and m is even, so we just make an entire list for this guy. And so for this hypothetical example with these counts, the answer would be 7. Yeah, that's basically how you do it, and I can show my code as well. Yeah, so I populate this counters map, and then here I handle the 0 case and then the self-inverse case. at the same time by just adding 1 to the result. And then here, I make sure to, uh, so like you have a pairing, and then one of these guys is going to be larger than the other. I make sure to only decrement one more than the minimum of the two, and then consider each one of the other subsequences that it can form separately. Yeah, that's basically how to do it. Let's now go to both parts of C, which I think was pretty cool. So yeah, let's start with C1, and then we can do C1 and C2, and then I can show my code, and that's pretty much it. So yeah, the problem is, so we fix k is equal to 3, and we want to find 3 numbers. Let's call them a, b, and c, such that a plus b plus c is equal to n, and the least common multiple of a, b, and c is less than or equal to n over 2. And we're given n, right? Yeah, and so this problem is mainly about casework. So the first thing you notice, right, is if n is like 3 or 6 or like 9, then you could just pick like 1, 1, 1, 2, 2, 2, or 3, 3, 3 respectively, right? So in particular, right, if n is equal to 0 mod 3, or sorry, n is congruent to 0 mod 3, then we can just pick n over 3, n over 3, and n over 3, right? Great. Let's say that it's not, right? But now let's say that we know that n is odd, right? So we know that n is congruent to 1 mod 2. Excuse me. So if we know that n is odd, right, then there exists some k, some integer k, such that n is equal to 2k plus 1, right? But then this is pretty straightforward. We can just pick k, k, and then 1, right? Because they add up to n, and clearly their LCM is equal to k, which is clearly less than n over 2. So basically now there's only one more case, or well, almost only one more case. So let's say that n is even, right? So we know that it's not equal to 0 mod 3, but we also know that it's even. So an example of like some of these numbers which fit this criteria are, let's say 4, 10, 16, and basically you can just keep adding on 6s to these, I think. Yeah, great. So now, like we can just use, yeah, we can just use like this definition of even, like we did in case 2, right? So let's say there exists some k1, uh, and I'm using k1 because we might have to do this again later. So let's say there exists k1 in z such that n equals 2k1, or like because it's even, we know that there exists a k1 in z such that n is equal to 2k1, right? So now let's just say, so let's suppose k1 is even, right? So if k1 is even, then there exists some k2 in z such that k1 is equal to 2k2, right? But then that means n is equal to 4k2, and so then we can just pick 2k2, k2, and k2, right? where in this case k2 is equal to n over 4. And so like n is equal to 0 mod 2 and k1 is equal to 0 mod 2. This just corresponds to n being 0 mod 4. Right. And I think I'll circle these choices, right? Yeah. Yeah, and so like we can pick 2 k2, k2, and k2 because they add up to n, and also because their LCM is 2k2, and 2k2 is exactly equal to n over 2. So we're fine there. So now the final case here is that k1 is congruent to 1 mod 2. And let's just do the same thing then, right? So let's just say that there exists some k2 such that k1 is equal to 2k2 plus 1, right? And so therefore n is equal to 2 times 2k2 plus 1, and this is equal to 4k2 plus 2, right? Did I do this right? I think, yeah. Yeah, this is correct. And so now we can just pick 2k2, 2k2, and 2, right? Because here their LCM is 2k2, which is less than n over 2, because because, because n over 2 would be 2k2 plus 1, right? Yeah. And so like we can write k2 in terms of n by just like solving for k2 in this equation, and then we can write yeah, so like everywhere where like we're picking k's instead of n's, we can just write it in terms of n, and that's how you can kind of implement this. And so like having walked through all of these cases, yeah, so like these are the 4 cases that the answer can be in, and the 4 choices that you can make while ensuring that the LCM is while ensuring that the conditions in the problem hold. And so I just want to talk about C2 real quick because it's very related. I actually didn't come up with this myself. I read it in the solutions, and I was mad at myself for not seeing this. But basically so the problem statement of C2 is that instead of fixing k to be 3, like k can now be like anything, right? And so here you want to pick some numbers a1 through ak such that their sum is equal to n, and then the LCM of a1 through ak is less than or equal to n over 2. But yeah, so the insight to this problem is to notice that like even so like for the first part, even like if you could pick 0, right, then like things are pretty straightforward, right? Like then you would just pick like n over 3, n over 3, n over 3, or n over 2, n over 2, and 0. But you can't pick 0. But the thing to realize is that for the second part, you can pick 1. And so basically the idea is that like you pick like you just keep picking ones for the first k minus 3 elements, and then you run uh, this algorithm from C1 to get the last 3 numbers, and then you run this algorithm with n minus k minus 3, right? Yeah, and then like you get a bunch of numbers. Yeah, and then you get a bunch of numbers which which satisfy these two constraints. And like initially when I saw this, I was trying to like generalize like some of this math that I was doing before, but like it really was a lot easier than this. You basically like use the first part while fixing like the first n-3 numbers to be ones. Cool. Yeah. Finally, I'll go over my code and then I'll end this video. Yeah, so basically, I wrote C1 and C2 in the same thing. So here, like, I have an assertion that K is 3, but I commented out for the second part. The main meat of the algorithm is here. So case 1, if n is 0 mod 3, then I just return n over 3, n over 3, n over 3. Here, if n is 0 mod 4, then I return n over 2, n over 4, n over 4. And if you solve these k values in terms of n and plugged it in, you would get the same thing. And then, let's see what else. Yeah, so here, if n is actually odd, then I return 2 times n over 4, 2 times n over 4. That corresponds to this case. And finally, if n is odd, then I return 1, and then this, which corresponds to k. Yeah, and then for the next part, I literally just pushed back ones until k minus 3, and then solved it for n minus the size of like how many ones I pushed. Cool. That's about it. Thanks for watching.